Let us start with the first chapter of second year mathematics. It is a continuation of the chapter Relations and Functions we studied in the last year. I am using only simple language that all of you can follow. Please be attentive. If you feel tired, take a pause for some time and then continue. Online classes give us enough freedom to watch the classes again and again when we wish. Today we are studying about the types of relations. Let us recall what we studied in our first year chapter. Relation means only connection in ordinary English. Mathematically, a relation from A to B is a subset of A cross B. Every relation from A to B is a subset of A cross B. Let us take an example. Let A equal to set 1, 2, 3. A contains 3 elements 1, 2 and 3. And let B equal to set A comma B. B contains 2 elements A and B. Let us write A cross B. A cross B equal to set of ordered pairs 1A, 1B, 2A, 2B, 3A, 3B. And the set A cross B contains 6 elements. Clearly, it has 2 raised to 6 subsets. That is, the set has 64 subsets. And some of them are written here. R1 equal to set 1A is a subset of A cross B which contains only one element. We can take another subsets like set 1B, set 2A, set 2B, etc. And similarly, R2 is a subset which contains 2 elements. There are many other subsets too which contain 2 elements. And R3 is a subset which contains 3 elements. We can write up to R64. Also note that all these relations, all these subsets of A cross B are relations to. Therefore, we can write R1, R2, R3, etc. R64. And surely one of them will be A cross B itself. Now, let us consider a set A equal to set 1, 2, 3. We have to define a relation in the set A. We have already studied last year that a relation in the set A is a relation from the set A to A itself. From the set A to A. A relation defined from A, set A to A is a relation in the set A. Or a relation in the set A is a subset of A cross A. Let us write all the subsets of A cross A. A cross A equal to set 1, 1, 1, 2, 1, 3, 2, 1, etc. 3, 3. Since A has 3 elements and again A has 3 elements, A cross A has 3 into 3 equal to 9 elements. The number of subsets of A cross A is a relation in the set A. And the number of subsets of A cross A is hence 2 raised to 9 equal to 512. Thus, A cross A has 512 subsets and each subset is a relation to. Let us list some of their subsets. R1 equal to set 1, 1. It contains only one element. R2 equal to set 1, 2. It also contains one element, etc., etc. R10, the 10th subset, 10 equal to set 1, 1, 1, 2. R11 equal to set 1, 1, 1, 3, etc. R10 and R11 contains two elements each, etc. Then three elements. And at last R511. R511 equal to set 1, 1, 1, 2, etc. 3, 3. It is the set A cross A itself, 511. A cross A itself. And there is also another relation, R5 term equal to 5, the null set. We know that null set is a subset of every set. Therefore, null set is a subset of A cross A2. Here, A cross A is the longest relation, and we call it the universal relation. A cross A is called the universal relation, and phi is called the empty relation. Then we have to know what a universal relation is and what an empty relation is. In a universal relation, here A5 level, in a universal relation, every element of A is related to every element of A. A cross A is the universal relation, and in a universal relation, every element of A is related to every element of A. And in an empty relation, no element of A is related to any element of A. In an empty relation, no element of A is related to any element of A. Thus, we have studied two types of relations. The first one is the universal relation, and the second one is the empty relation. Now, we have to study what an equivalence relation is. We have to study in detail what an equivalence relation is. And it is the most important one we have to study in this chapter. A relation in the set A is said to be an equivalence relation if it is a reflexive relation, a symmetric relation, and a transitive relation. A relation in the set A is said to be an equivalence relation if it is reflexive, symmetric, and transitive. Now we are going to study in detail what an equivalence relation is. Thus we have to discuss what a reflexive relation, what a symmetric relation, and what a transitive relation is. Let us start with a reflexive relation. In the set capital A, every element A belongs to every element A belongs to capital A is related to the element A itself. If every element in the set A is related to the same element, it is called a reflexive relation. Thus, a relation in the set A is said to be a reflexive relation if every element A is related to itself. Now, we are going to define what a symmetric relation is. A relation in the set A is said to be a symmetric relation when the element A is related to B, and if B is related to A, the relation is said to be a symmetric relation. When A is related to B, then B is related to A, we say it is a symmetric relation. Thus, the definition of a symmetric relation is that when the element A is related to B, then the element B should be related to A. And the third one is a transitive relation. A transitive relation is a relation such that if the element A is related to B and the element B is related to C, and if then the element A is related to C, then the relation is said to be a transitive relation. Once more, the first one is a reflexive relation. Consider this set A. If every element of A is related to N itself, the relation is said to be the reflexive relation. We write A or A. A is related to A. We are going to explain a reflexive relation in detail. Consider the set A equal to set 1, 2, 3. We discussed earlier A equal to set 1, 2, 3. We have across A equal to set 1, 1, 1, 2, 1, 3, etc. 2, 3, 3. Across A contains 9 elements. And we know that every subset of across A is a relation from A to itself. Now, consider a subset of A cross A. R equal to set 1, 1, 1, 1, 1, 2, 2, 1, 2, 2, and 3, 3. We have taken only 5 elements. R equal to set 1, 1, 1, 2, 2, 1, 2, 2, 3, 3. Clearly, it is a subset of A cross A. And we have defined what a reflexive relation is. A reflexive relation is a relation in which A belongs to R, ordered pair A belongs to R for every A belongs to A. For every A belongs to capital A. If for every element in A, if A belongs to R, it is a reflexive relation. It is not tough as we think, it is a simple thing. That is, A is related to A. The element is related to itself for every element. Here we have 1, 1 is there in the set R. 2, 2 is there in the set R. 3, 3 is also an element of R. Thus, every element is related to itself. 1 is related to 1, 2 is related to 2, and 3 is related to 3. Whatever the other elements are, it is a reflexive relation. Since it is a reflexive relation, it should contain 1, 1, 2, 2, and 3, 3 for every element. Can you say, now whether it is a reflexive relation? 1, 1, 1, 2, 2, 1, 2, 2. Can you say whether it is a reflexive relation? Clearly, it is not a reflexive relation. It contains 1, 1 and 2, 2, but it does not contain 3, 3. We have defined that for every A belongs to A. A has 3 elements, 1, 2, and 3. Therefore, 1 should be related to 1, 2 should be related to 2, and 3 should be related to 3. And it is necessary that there should be 3, 3 for it to be an equivalence relation. Thus, again we explain the definition of a reflexive relation. Again we explain the definition of a reflexive relation. If a relation in the set A is a reflexive relation, then A is related to A, or A belongs to R for every A belongs to A. Thus, if A equal to set 1, 2, 3, then 1 should be related to 1, 2 should be related to 2, and 3 should be related to 3 for it to be an equivalence relation, for it to be a reflexive relation. The next one is a symmetric relation. By definition, a relation in the set A relation R in the set A is said to be a symmetric relation if whenever AB belongs to R, or whenever A is related to B, then BA should belong to R. BA should belong to R. That is, B should be related to A for every. Here we have 1, 2 belong to R. 1, 2 is an element of R. 1, 2 belongs to R. Then 2, 1 also belongs to R. Whenever 1, 2 belongs to R, then 2, 1 also belongs to R. Therefore, the relation is symmetric to. Whenever AB belongs to R, then BA should belong to R. The relation is said to be a symmetric relation. When an element A is related to B, then B should be related to A. It is a symmetric relation because whenever the first element is related to the second element, then the second element is also related to the first element. Here, whenever 1 is related to 1 in the reverse order, 1 is related to 1. Whenever 1 is related to 2, 2 is related to 1. When 2 is related to 2, then 2 is related to 2. Whenever 3 is related to 3 in the reverse order, 3 is related to 3. Thus, the relation R is a symmetric relation also. Also, let us explain what a symmetric relation is. Let us come to the formal definition. Whenever AB belongs to R, then BA belongs to R. Whenever AB is an element of R, then if BA is also an element of R, it is a symmetric relation. That is, whenever A is related to B, then B is related to A also, then it is a symmetric relation. The next one is a transitive relation. A transitive relation is one if AB belongs to R, that is A is related to B and B is related to C, then A should be related to R. A should be related to C. For example, whenever 1 is related to 2 and 2 is related to 3, then 1 should be related to 3. R equal to set 1, 2, 2, 3, 3, 3, 1, 3 is a transitive relation because whenever 1 is related to 2 and 2 is related to 3, then 1 is related to 3. Consider another relation R equal to is this relation reflexive? It is clearly reflexive. On the set A equal to set 1, 2, 3, the relation is a reflexive relation because the relation contains the elements, contains the ordered pairs 1, 1, 2, 2 and 3, 3. Is the relation symmetric? It is not symmetric because whenever 1 is related to 2, 1, 2 is an element of R, but 2, 1 is not an element of R. Therefore, it is not a symmetric relation. Is it a transitive relation? It is not a transitive relation because 1 is related to 2 and 2 is related to 3, but 1 is not related to 3. That is, 1, 3 is not an element of R. 1, 3 is not an element of R. This relation is not a transitive relation. Thus, a relation is said to be an equivalence relation if R is reflexive, R is symmetric, and R is transitive. Please look at this problem. Let R is a relation defined in set 1, 2, 3, 4 given by R equal to set 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, 3, 2. Choose the correct answer. R is reflexive and symmetric but not transitive. Reflexive and transitive but not symmetric. Symmetric and transitive but not reflexive. And the fourth option is R is an equivalence relation. Let us check it one by one. Is the relation reflexive? Yes, it is reflexive. Therefore, 1 is related to 1. Since 1 is related to 1, 2 is related to 2, 3 is related to 3, and 4 is related to 4. It is a reflexive relation. Each element of the set is related to itself. Therefore, it is a reflexive relation. Is it symmetric? Is it a symmetric relation? Let us check. 1, 3 belongs to R and 3, 2 belongs to R. If it is a symmetric relation, if 1, 3 belongs to R, then 3, 1 should belong to R. There is no 3, 1 in this set. And 3, 2 belongs to R, but 2, 3 does not belong to R. There is no 2, 3 in this set. Therefore, clearly it is not symmetric. Let us check whether it is a transitive relation. We have 1, 3 belongs to R and 3, 2 belongs to R. If it is transitive, by definition, 1, 2 should belong to R. Here, 1, 2 belongs to R. And we can check for other elements too. Therefore, it seems to be a transitive relation. And it is reflexive, not symmetric, and transitive. Then which is the answer? It is not an equivalence relation since it is not symmetric. Therefore, the answer is option B. Let R is another relation in the same set given by R equal to set of all AB such that A less than or equal to B. We can write this relation in roster form as R equal to. We have to write all the elements of this set. Since 1 less than or equal to 1, 1, 1 is an element of the set, and 1, 2, 1 less than or equal to 2, and 4 less than or equal to 4. Thus, there are 10 elements in the set R. We can check one by one whether the relation is reflexive, symmetric, or transitive. Clearly, it is a reflexive relation. Why? 1, 1 belongs to the set. 1 is related to 1. 2, 2 belongs to the set. 2 is related to 2. 3 is related to 3. And 4 is related to 4. Therefore, clearly it is a reflexive relation. Is it a symmetric relation? It cannot be a symmetric relation. Why? The element 1, 2 is an element of R. 1, 2 is an element of R. But 2, 1 is not an element of R. 2, 1 is not there in this set R. Therefore, it is not a symmetric relation. Similarly, for 1, 3 there is no 3, 1 in this set. For 1, 4 there is no 4, 1 in this set, etc. It is not a symmetric relation. Is it a transitive relation? Just check. 1, 3 belongs to R. 1, 3 is an element of R. 1, 3 belongs to R. 1, 3 is an element of R. And 3, 4 belongs to R. 3, 4 is an element of R. 3, 4 belongs to R. We have to check whether 1, 4 belongs to R. Yes, there is 1, 4 is there in the set R. Therefore, 1, 4 belongs to R. 1, 4 belongs to R. 1, 4 belongs to R. Therefore, the relation is a transitive relation. Thus, the relation is reflexive, not symmetric, and transitive. Hence, it is not an equivalence relation. Now, let us extend this question for an infinite set. Let us, here 1, 2, 3, 4, set 1, 2, 3, 4 is a finite set. If we replace set 1, 2, 3, 4 by an infinite set like R, set of real numbers, or N, the set of natural numbers, etc., we can make another question. Let R is a relation defined in N, the set of all natural numbers N, given by R equal to set of all AB such that A less than or equal to B, A comma B belongs to N, the set of all natural numbers. Since N is not a finite set, we can prove that it is whether it is a reflexive, symmetric or transitive relation generally. As we have done in the previous question, we cannot list all of the elements of R. Now, to prove that it is a reflexive relation, we write, for a reflexive relation, the element should be related to itself. Here we write A is related to A. That is, AA belongs to, since AA belongs to R, since AA belongs to R. Why AA belongs to R? Since A is less than or equal to A, we can write A is less than or equal to B. For A is less than or equal to A, we can write AA, set AA belongs to R, ordered where AA belongs to R. Therefore, the relation is a reflexive relation. Is it symmetric? Let AB belongs to R, that A less than or equal to B, then B cannot be less than or equal to A. A less than or equal to B does not imply B less than or equal to A. Therefore, A is related to B. AB belongs to R does not imply BA belongs to R. B cannot be less than or equal to A. Therefore, all elements. Therefore, it cannot be a symmetric relation. Can it be a transitive relation? Let A is less than or equal to B. A less than or equal to B, and let B is less than or equal to C. If A less than or equal to B and B is less than or equal to C, clearly A is less than or equal to C. A less than or equal to C. Thus, if AB belongs to R, AB belongs to R here means A is less than or equal to B, and BC belongs to R here means B is less than or equal to C. Then this implies AC belongs to R. That is, A less than or equal to C. Therefore, the relation is a transitive relation. Thus, the difference between the previous problem and this problem is that we cannot we cannot list all the elements of the set R. Therefore, we have done it theoretically. Since A is less than or equal to A for any A, for every A in this set, for every natural numbers, AA belongs to R. Therefore, the relation is reflexive. A less than or equal to B does not imply B less than or equal to A. If A is less than or equal to B, it does not imply B is less than or equal to A. Therefore, it is not symmetric. It is transitive because A is less than or equal to B, that is AB belongs to R, and B is less than or equal to C implies A is less than or equal to C. Therefore, it is a transitive relation. Thus, the relation is reflexive, not symmetric, but transitive. Let us solve a similar problem. The question is that on R, on the set of real numbers, if the relation is given by the relation R equal to set of all xy such that x equal to y, show that the relation is an equivalence relation. It is a problem similar to the above problem. Answer is that since x equal to x for all x belongs to R, for every x it is equal to x itself. That is, x belongs to R. Therefore, the relation is reflexive. Now, if x equal to y, then clearly y equal to x. For every x, y belongs to R, the relation is a symmetric relation. And to show that it is a transitive relation, if the element x equal to y and the element y equal to z, then clearly x equal to z for all x, y, z belongs to R. The relation is a transitive relation. Clearly, the relation is an equivalence relation. We are going to check whether parallelism or perpendicularity defined on the set of all straight lines in a plane is an equivalence relation. Let in a plane, on this plane, that there are many straight lines. And let us take three parallel lines, three lines A, B and C. Three lines A, B and C. Here, since a line is parallel to itself, A is parallel to A itself. Therefore, the relation is reflexive, clearly reflexive. For any A, for any straight line, the line is parallel to itself. Therefore, the relation parallelism is reflexive. Now, if A is parallel to B, then clearly B is parallel to A. A parallel to B implies B parallel to A. Therefore, the relation is symmetric. And to check whether the relation is transitive, let A is parallel to B, A parallel to B, and B is parallel to C, B is parallel to C. Is A parallel to C? Yes, A is parallel to C. It implies A parallel to C. Thus, the relation is transitive. It is a reflexive parallelism. It is reflexive, it is symmetric, and it is transitive. Thus, the relation is an equivalence relation. Parallelism of all straight lines drawn in a plane is an equivalence relation. But it is not the case of perpendicularity. Perpendicularity is not an equivalence relation. A line cannot be perpendicular to itself. The relation is not reflexive. If the line A is perpendicular to B, then the line B is perpendicular to A. The relation is symmetric, but it is not transitive. Why? If A is perpendicular to B and B is perpendicular to C, then A is not perpendicular to C. Now we are discussing the most important property of an equivalence relation. An equivalence relation partitions the given set into mutually disjoint equivalence classes. An equivalence relation partitions or subdivides the given set into mutually disjoint equivalence classes. Let us explain the idea with the help of an example. Let A equal to set 1, 2, 3. R is a relation defined in A which contains the ordered pairs 1, 1, 2, 2, 3, 3, 1, 2 and 2, 1. Clearly it is an equivalence relation, we can check. It is reflexive, 1, 1, 2, 2, 3, 3 belongs to the set, it is reflexive. Whenever 1, 2 belongs to the set, 2, 1 is also there in the set, it is symmetric. And it is transitive too, 1, 2, 2, 1 implies 1, 1 belongs to the set, etc. Therefore, it is an equivalence relation. We have to check how this equivalence relation partitions the set A into equivalence classes, mutually disjoint equivalence classes. See, here the element 1 is related to 1, 2 is related to 2, 1 is related to 1, 2 is related to 1, also 1 is related to 2 and 2 is related to 1. Thus, there is an interrelationship among the members 1 and 2. 1 is related to 1, 2 is related to 2, 1 is related to 2 and 2 is related to 1. But 3 is an isolate, 3 is related to 3 only. If we denote A as I said, we denote equivalence class containing 1 as class 1 equal to the elements related to 1, that is 1 and 1 is also related to 2. Therefore, equivalence class 1 contains 1 and the elements related to 1, that is 1 and 2. And next one is, we need not write equivalence class 2 since equivalence class 2 contains the same elements 1 and 2. The next one is equivalence class 3. Class 3. Class 3 contains only the elements related to 3. 3 is an isolate. 3 is related to 3 only. Therefore, equivalence class 3. Class 3 equal to set 3. Singleton set 3. Also, A contains 3 elements 1, 2 and 3. 1 and 2 are interrelated. Therefore, it is a class. It is a class. 1 and 2 is a group. And 3 is an isolate. 3 is a single element in it. Also, these two classes, union of these two classes, class 1 union class 3 gives the given set A, represents the given set A, set 1, 2, 3, and their intersection, class 1 intersection class 3 equal to 5, equal to empty set. Empty set. As the classes class 1 and class 3 have no elements in common, class 1 intersection class 3 equal to empty set. Thus, we have subdivided the given set A into two mutually disjoint equivalence classes as their union is the given set and their intersection is 5. On the board, you can see a figure. The picture represents a classroom containing only 10 students. Usually in a classroom, there are some peer groups or gangs. One student in a gang is usually related to all other students in the gang. Such simple gangs, such subgroups are called equivalence classes. And the union of these 4 equivalence classes is the classroom itself. You have heard a film song. 1 plus 1, 2 is maths. 1 plus 1, 1 is love. When one in the group loves each other, it really becomes a peer group. See, mathematics is not only about numbers as the poet implies. Now, modern mathematics deals with social relations too. The section Types of Relations is completed, and I have attached some assignments for you. Please take a piece of paper and do all these assignments. And if you feel that you are not clear about the ideas described in the chapter, please go through the class again. Also, I have attached some problems, worked out examples in the description section which are important in the examination point of view. Please take it serious, and thank you.